Hello and welcome to the wonderful world of electronics. If you've been following this video lecture series, you've probably hit that subscribe button with joy already. If this is your first time viewing us, then perhaps you may need to go and look at some of the previous lectures so that this will be most beneficial to you. In any case, welcome. Today we are going to take a look at how to find voltages and currents within a network that contains two voltage sources. So this is a sort of generic network laid out here. We've just indicated the resistors, the polarity of the voltage sources, and we've picked some current directions and put them on. And as you can see, we've written some equations which we're now going to explain to you. The first thing you need to know when analyzing these type of problem is the rules. First of all, current flows from positive to negative in our system. So as shown there on the right, if the current is entering a resistor, it's going to be more negative when it comes out than when it went in. Current going into a node, and as you can see, a node is where any two wires join together. We have a node clearly labeled there at the top where we have three wires connected by a point. Current going into the node, where the arrow is pointing into the node, is taken as negative, and when it comes out of the node, it's taken as positive. Now you notice that we have two loops there, or circuits as they would be called, and we have two clockwise arrows marked equation 1 and equation 2. And when we go around that loop or circuit, we always go in the clockwise direction. That way we can be consistent. We need to be consistent, otherwise we will confuse ourselves. It doesn't mean that you have to go around it in the clockwise direction, but if you choose to go around one in the clockwise direction and the other in the anti-clockwise direction, and you don't make the proper compensation, your result will obviously be wrong. So by establishing a standard and sticking with it, you're more likely to get consistent results without confusing yourself. So that is why most textbooks recommend that you should, in fact, pick a clockwise direction for consistency. Okay, now it doesn't matter where you start in the loop. We can start from the voltage source, we can start from one of the resistors. We're going to get the same results. The terms will just be ordered in a little different order in the equation. And finally, we need a convention when passing through the various parts. And the established convention is that when we move from positive to negative, we take that term in the equation as positive. So if we go through a part and we're moving from positive to negative, it's a positive term. And if we go through that part in the clockwise direction and we're moving from negative to positive, then the term that's represented by that part is negative. Okay. So I've drawn some circles there to show you what I mean. In the case of R2, we are going in a positive direction, and that's the term represented there by I1 R2 with a positive sign in front of it. Now over here we've drawn some directions. As you can see, since we're going around in a clockwise direction, when we go through the V2 source or the V2 part, we are going in a positive direction. That's why the V2 has a plus sign in front of it. And when we're going through the V1, we're actually traversing the part in the clockwise direction from minus to plus, which is why the V1 has a minus symbol in front of it. Now, once you've written down these three equations, the equations of the two loops and the equations of the node, you really have all you need, and the rest is just mathematics. But it's important, really important, to get these three equations correct. Otherwise, all your mathematics is going to lead to totally incorrect answers. So if you're not fully understanding how we are processing these two circuits and creating our equations, then you need to study this first part until you're absolutely satisfied in your own mind that you can move forward. Now, once we have established the equations that we want, as you can see here, we can do an example. Now, here's an example where we have substituted actual resistor values and voltage sources that are actually labeled with specific voltages as opposed to generic symbols. Okay? So we've taken loop 1 there. We've written the equation for the node. For this problem, we have included an I in the actual original problem in black. We are hoping to find out what that current is, that I current that's flowing into the 4 ohm resistor. But we need to label the other currents, so I've just put on some directional symbols there, and I've labeled one I1 and the other I2. Now, it doesn't really matter how you label these, or even what directions you put on the purple arrows. It would be helpful to put them on in a direction that represents the actual current flow, but you may not be absolutely sure what the direction is in some cases. So if you put on an arrow backwards, it shouldn't really cause a problem if you still follow the rules that I have given you before. So you can swap the I1 and the I2 if you want, or even the loops. But once you have put on the arrows, you then can label the plus side of your resistors. Based on the fact that the current is flowing into that end, it would have to be positive. So we've done that. And we've also written the equation for loop 1. So hopefully you're happy with that. If not, study it some more till you actually figure it out. And here is the loop 2. And now we have all we need, and the rest is mathematics. Now, what do we want? We want to find I. And we have actually 3 unknowns, but 2 equations. So what we're going to do is we have enough information that we can substitute here and get actually 2 unknowns. Okay? So we can substitute I. As you can see, it's not very helpful, so we rearrange that node equation so that the I is going to remain in our final 2 equations. So as you can see now, when we actually substitute, we're left with I and I2, and I1 disappears. You don't want the variable that you're trying to find, you don't want that to disappear. I mean, even if it did, you could probably get it back by using the node equation at the end. But you want to have your I in your actual equations. So once we have made that substitution, we have dismissed I1, and now we have I2 and I in our equations. Now we're going to further massage these equations, simplify them, and rearrange their terms. Now if you look closely at what we've done here, we have the I's under each other, we have the I2's under each other, and we have the constants over on the right hand side of our equal sign. We've moved the constants out of the equation from the 0 over to the left to the right hand side, and we've got our i's lined up. So that allows us to do something really neat. That allows us to put our equations into a matrix. On the left we have a 2-square matrix, and on the right we have a constant vector, as you can see. Now, why would we want to do this? Well, the Cramer's rule, which is the one I'm going to show you, needs it in this form. But even if you were not using the Cramer's rule, if you were using a calculator that's capable of solving simultaneous linear equations, you would still have to enter the coefficients. That left-hand matrix is a coefficient matrix, and the constants in this order into your calculator to be able to get your solutions. So whether you're using some other method or not, it's preferable to set up your equations in this fashion. So we're going to explain this Cramer's rule solution to you, and it's fairly simple to follow, particularly in the 2-equation case. But if you prefer to use another method, that's quite up to you. So what we've done here now is we've worked out the determinant of our coefficient matrix. Okay, every matrix has a unique determinant, and the expression that I've shown here shows you how to work it out. If you have a calculator that does vectors and matrices, chances are it can work out the determinant for you at the push of a button. If not, you just have to cross multiply and do it as it's shown here to get your determinant. Now, once we've got the determinant, we have to substitute our constant vector into a column of our coefficient matrix. And we're going to show you how to do that. Once you see the procedure, you should be able to do it with ease. We just replace the first column of the matrix with the vector, calculate a determinant. Then we replace the second column with the vector and calculate another determinant, as you'll see in the last slide. So now we come to the final slide, and we're going to see the final solution. There is our first determinant. Now here we have replaced the first column with the constant vector and done another determinant. We've replaced the second column with the constant vector and worked out the third determinant. And now we calculate our I and our I2 by simply dividing by the determinant that we got from the coefficient matrix as shown. Now you would realize that we were solving for I1 and I2 in our initial equations. We can easily now get I and I2. We can easily get the I1 now from the node, but we didn't actually need. One of the nice things about using the Cramer's rule solution is that you may not have to do all of them. We certainly did not need to do the last line because we weren't trying to find out I2. We only wanted I. So if you organize your matrix correctly, you probably do not have to find all of them. And this is useful in larger systems where you have more i's to find. You can have 3, 4, or 5 i's to find, and then it gets really tedious to have to work them all out and work out all these various determinants. So if you arrange your matrices properly, and you don't need all of the i's, then you probably don't have to follow the whole thing right away through. So we could have omitted that last line entirely, and we would have been good to go. Now the other thing that I need to tell you before we close the video is that you observe that your answer is negative for I. Now, it is important that you know that negative signs on currents merely mean that the direction of the current is opposite to the way you had used it in your calculation. So therefore, in actual fact, that black arrow that we put on the initial problem for you to solve is pointing the wrong way. With the values of those sources and resistors, the actual current that will flow is going to flow in the opposite direction to that black arrow, and that is why we have ended up with a negative sign in front of our current. Thank you for watching the Stephen Mendes channel. Thank you for watching our lecture series on electronics, and we'll see you in the next video.